Now we have the equation of motion of the simple pendulum. This equation, okay. It seems this equation looks simple, but if we want to solve this equation directly, it can be quite difficult because this is a nonlinear equation. The nonlinearity comes from the term sine theta. Equation contains the term that is not linear in theta, this term. So it becomes the nonlinear equation, and we will not solve this directly because we need an advanced technique in mathematics to do so. Anyway, we can do an approximation to make this equation much more simpler, and we can solve it very easily. The approximation is like this. Okay. We call this the small angle approximation. Small angle approximation. The small angle approximation is that if the theta that involved with this pendulum is small, it means that we do not pull the mass m away too much from the equilibrium point. So if we have this condition that is theta is much less than 1, but be careful on this. What is 1 here? You have to specify that it is 1 radian. That is, if theta is much less than 1 radian, for example, it's 0.1 radian or 0.01 radian, something like that, and you can say that, okay, we can use the small angle approximation. But 1 radian is about 60 degrees. So if theta is about 5 degrees, we can assume the small angle approximation also. So you have to be careful when we say that theta is small. Small with respect to what? It's small with respect to the radian, the angle in radian. Okay. So if theta is small, we can do this approximation, that is sine theta is approximately equal to theta. Okay, sine theta is approximately equal to theta. This comes from the calculus. In the basic calculus, you should learn this limit, that is limit of x equal to 0 of sine x over x is equal to 1. So it means that if x here is small, it means it's close to 0, the ratio between sine x and x is equal to 1, which means that sine x is equal to x. And we use this relation to do the approximation that if theta is small, sine theta is equal to theta, is approximately equal to theta. So if we put this into the equation of motion, we will have that d square theta by dt square is equal to the minus of the g over L of theta. Okay, under the small angle approximation, we have this d square theta by dt square is equal to the minus of g over L theta. And you can see that if we compare this equation with the equation of the mass spring system, d square x by dt square is equal to the minus of kx. So you can see that if you replace x with theta, and you replace k with g over L, you will have the same equation. And if you have the same equation, you will have the same solution. So from this analogy, we can say that the solution of this equation is like this. The solution that is theta t is equal to the theta max of psi omega t plus phi, and the omega is equal to, oh, I missed this term. This has to be over m. Okay. Now we have that the omega is equal to the square root of g over L. Okay, in analogy with the omega is the square root of k over m in the mass spring system. Okay, so we have the omega is equal to the square root of g over L, and the theta, the angle theta, is oscillate, or it is a sinusoidal function as in the oscillation of the mass spring system. And from this expression of the angular velocity, angular frequency, we can say that the period of the motion is 1 over f, which is the 2 pi over omega, and it is 2 pi of the L over G. We can see that the period of the pendulum is independent of the mass. So if we have the pendulum with the same length L, and if we assume that G is a constant, so we will have the same period no matter the mass m we use. So this is very useful because in the past we used the pendulum as a timekeeper or as a time base for the clock. Okay, because you can see that if we have the same length of L, the pendulum will swing back and forth with the same period. So we can use that period as our time base. Okay, and that is the principle of the old-fashioned clock.